All right, hello everyone. It's May the 16th. All right, let's do this. Swap nodes in pair. Given a linked list, swap every two adjacent nodes and then return its head. You must solve the problem without modifying the values. Swap every two adjacent nodes. So if this, I need to swap to this. This and this swap this. How about it? What if it's 5? What if it's 5? What's gonna do? 5, I think the last one just ignored. Yeah, the last one ignored. Okay. So, we can swap. Basically, we want to swap, and then we progress, right? So it's not supposed to be too hard. But like always, we will have a dummy at the front. Usually a dummy is always helpful. Okay, so we can say we can have pre. Shouldn't call it pre. I should call it. I call it N1 and N2. Okay, node 1, node 2. That's how we start. I want to swap these two. So what we can do is take this as a temp. Okay, this is what we say temp equals n2.next. Okay, and then we say n1.next equals temp. So basically we say this one pointing here, right? And then temp.next. Ooh, temp.next. Huh. We need to notice this one as well. You know what? Maybe we should set this one to temp. Let me think. Or we can move this one here first, right? We can say n1.next, that's n1.next equals temp.next. Okay, so this one pointing here, n1.next equals to this, and then temp.next equals n2. Oh, this is actually n2. Right, n2.next is temp, and n2.next pointing to temp.next, and then n1.next equals to temp. This is temp, and then temp.next equals 2 and 2. So okay, so we restructure the thing, and when we restructure, n1 shall equal to n1.next. So n1 coming here. n2 does not change position. Wait, really? We have d to 2 to 1 to 3 and 4. So this is n1. This is temp. This is n2. So n1 move forward. n2 does not change. That doesn't feel right. That does not feel right. Then what? Then what do you do? Oh, then you need to walk both of them forward. n2 walk forward once, n1 walk forward twice. Now you do the swap. Okay, so let's try one more time. T, this is T, n2.next, so this one will point into here, which is none. And n1.next will equal to T, so this one will point into here. And then T.next point into here. Okay, so when we swap, that will be 2, 1, 4, 3. n2 will be here, right? And n1 still here, t is here, and then this is none. Then we need to n2 move forward, n1 move forward twice. And then n2 is none, so we terminate. If we have another one, let's say we have a 5, right? If we have a 5, then t is none. Well, we might actually do one more time. Hold up. T is none. T is none, then that should be. So n2.next. So while n2, okay, so while n2 and n2.next. Yep, that shall be the thing. Oopsie doozy. Shoot. All right, let's do this. All right, dummy equals list node next equals head. Okay, n1, n2 equals dummy and head, while n2 and n2.next. T equals n2.next. And then tn2.next, n2.next, n2, n1, n2, n2.next equals to t.next, right? n1.next equals to n1.next equals to n2, and it was a t. Wait, hold on. Yeah, n1.next equals to t, and then t.next equals to t.next equals to n1.next, which is n2. Yes, which is n2. Okay, so we're done, right? And then n2 equals n2.next. n1 equals n1.next. Then we return dummy.next. Okay, let's see if this one works. Seems to be good. Okay. All right, done with this. Let's try this one. Find score of an array after marking all elements. You're given an array consisting of positive integers. Okay, starting with score 0, apply the following algorithm. Choose the smallest integer that is not marked. If there is a tie, choose the one with the smallest index. Add the value of the chosen integer. Mark the chosen element and its two adjacent elements if they exist. Repeat until all the array elements are marked. Return the score you get. We mark the element as, so 1 is the smallest unmarked. So we mark it and it's 2 adjacent. 2, the smallest unmarked. So we mark it and 1 adjacent. And then 4. All right, so it's definitely priority queue, right? So priority queue will do the number and index, right? So the first one pop out. We also need to have an auxiliary array says marked. Yeah, this one is actually not that hard. All right, so import heap queue. All right, so we need, well, nums will be, no, heap, we need a heap. For in enumerate nums, heap q.heap push, heap n first and I. And then we need marked, right? Marked shall be not marked times this. All right, while and rest equal to 0, while heap, right? Because you pop things out. While heap, index n equal to heap q dot heap pop heap. Okay, if marked I, if not marked, then rest plus equal to n, and then marked I equal to marked I equal to 1. If I minus 1 large equal to 0, marked I minus 1 equal to 1. If I plus 1 is smaller equal to, is smaller than len nums, marked I plus 1 equal to 1. Right? And then return the rest. I think that shall do. Second one is not right. Interesting. Doesn't matter. We'll figure it out. 2, 3, 5, 1, 3, 2. Interesting. So the first one is 1, second one is 2, the smallest. Yeah. And then the last one is 2. What did I get? I get 1, yeah. And then I get 2, 0. Yeah, that's 3. And then I get this 2, 5. 0, 1, 2, 3, 4, 5. Yeah, that should be it. What did I get all the rest? Huh? The hell? Two, 0. I did not. Oh, dude, N and Y. Sorry, it was a typo. That doesn't make any sense. Priority queue. ON log n. Yep, that should be good. Okay, this one's done. Minimum time to repair cars. You're given an integer array ranks representing the ranks of some mechanics. Ranks I is the rank of the ith mechanic. A mechanic with the rank R can repair n cars in r times n squared minutes. You're also given integer cars representing the total number of cars to be repaired and the minimum time taken to repair all the cars. All the mechanic can repair the car simultaneously. So we have the rank. Ranks R is the ith, with the rank R can repair R times n. What's n? Is n the size? The first will repair 2 cars. Oh, n is the number of cars to repair. So this, the second will repair 2 cars. The third repair 2 cars. And the fourth repair 4 cars. Okay. Let's see. We have 4, 2, 3, 1, and 10 cars. Okay, I have 10 cars. So we want to find out the minimum time taken, and then they can all do it at the same time, right? They can all do it at the same time. So each one we can, I mean, we want the one with the, so ten cars, right? Minimum time. Maybe this is binary search. I want to try binary search. Okay. Binary search is the minimum time, right? So we say we want a time and we see if it's possible. So let's say we have a time. Well, the max time, the min time is 1, right? So the min time is always 1. The max time, oh, that's actually interesting. What is the max time? Max time is the highest rank, or the highest R. Multiply, we'll have that fix all the cars, right? So it'll be 400. So now the first order is, let's say the mid is 200. So we say if 200, can we do 200 here? Well, if it's 200, we can say, what's the max number the first one can do? Well, the max number the first one can do if we give 200 is 200 divided by 4. And then we do square root. So it's square root 50, right? What's square root 57? And then 200 divided by 2 is 100. So it's 10. Boom, it's already larger, so we can do it. So we go down to 100, okay? So now mid equal to 100. The first one is 5. Second one is 7. Boom, larger than 10. So now we do mid is going to be 50. 50, what's 50 divided by 4? 50 divided by 4. Now, when it's not divisible, what do you do? Well, I mean, we want to find the largest n such that the value is smaller or equal to 50. It cannot be larger than, right? So 50 divided by 4 is that 15? No, 15 is 60. 12, right? 12 is 48. So we do, because 13 will be more, so 12. So square root of 12, that's 3. And then 50 divided by 2, that will be 5. 50 divided by 3 is going to be 16. So that's 4. And it's larger than, so now we say mid equals to 25. Right, we just go all the way down to find the one that works. Yep, I think that shall be the solution. No wonder it's changed to be a medium question. Maybe this one originally was not a medium question. Okay, so we need to do low, high equal to low. Low is always going to be 1. High, actually, let's do low equal to 0. High is going to be max ranks times cars squared plus 1. while low is smaller than high, mid is low plus high, and current cars 0, and then for R in ranks, current car shall equal to plus equal to mid divided by R, and int is QRT this, right? And if cos is larger than cos, break. Okay, so else, which means it's never, so it's small, too few cars, so we need to give bigger. So low plus low equals mid plus 1, and continue. All right, otherwise then high equals mid. So blah blah blah, we want to find the smallest, which means when we get out is the low is not working, right? It's not working, so we plus, and then so we shall return low. This is low. Right, give us a shot. 4 2 3 1 10 16 5 1 8 6 16. Ranks cars, pair cars, ranks and cars. That is very bad. Interesting. What happened? Let's take a look. Low, high, and mid. Okay, start with this. Okay, so 12. 12 is bad, so we do 13. And a 16. Right, 16 is good. Wait, 16 divided by 4. You know what? Let me check this. Actually, can I even check? Doesn't matter. We do this current cost. We do it 2 times. All right. So when it's 16 is 10, right? 16 is 10, which means it's good. So shouldn't high equals mid? Current cost is 10, right? We didn't break. If we didn't break, we should go for else. Oh yeah, low is low plus equal 1. Wait, you want a minimum time, right? You want a minimum time. So if the current time is good, wait, why you go up if the current time is good? We want a minimum time, right? So if the time is good, we shall reduce, right? The time is good, we reduce. If the time is equal, we shall reduce. We shall reduce. That's the reason. Because it's good, so we can go down, right? There we go. That's that. we want to try just for fun. Okay. All right. This is just binary search. Yeah, you can use bisect left. Yeah, but bisect left is require a little bit. I is QRT. There is a I is QRT. What? What the hell? There is a I is QRT. Dude. Dude, I is QRT. I never heard of it. I is QRT. Oh my goodness, it's real. New inversion, return the integer square root of non-negative. This is oh my word. Oh. Oh, that's probably a link. That's not a link. All right, that's it. I mean, we can do this, but nah, that's all right. And this is not n, right? This is m, because you're doing this. Where m equal to maximum. Oh, how can't you do this? This is the maximum possible. Okay. And max ranks. All right, that shall be it. Good. All right, that will be it.